Are we alone in the universe? This question has fascinated humanity for centuries. It's a query that has not only captured our imagination, but it has also driven our scientific pursuits and exploration. From the earliest astronomers gazing up at the heavens to the cutting-edge research being conducted today, the possibility of extraterrestrial life has been a central question, a mystery begging to be solved. Throughout history, this question has permeated our culture and our consciousness. From ancient myths and legends to modern science fiction, the idea of life beyond our planet has been a constant source of wonder and speculation. It has inspired countless stories, artworks, and even philosophical debates. It's a question that pushes the boundaries of our understanding and challenges us to think beyond our own existence. This question has also been a catalyst for scientific research and exploration. It has driven the development of technologies, theories, and missions aimed at probing the mysteries of the universe. From the invention of the telescope that allowed us to peer deeper into the cosmos, to the launch of spacecrafts destined for the furthest reaches of our solar system, the quest for extraterrestrial life embodies our innate curiosity and our relentless drive to understand our place in the universe. But how do we even begin to tackle such a monumental question? How do we sift through the vast expanse of stars, galaxies, and potential planets to find signs of life? This is where science steps in. Using sophisticated tools and methodologies, we've begun to navigate the cosmos, searching for hints of life beyond our own planet. One such tool is the Drake equation. It's a mathematical formula that estimates the potential number of extraterrestrial civilizations with which we might come into contact. While it doesn't provide a definitive answer to our question, it offers a framework to guide our search and spark further investigation. As we delve into the vast expanse of space, we use scientific tools like the Drake equation to estimate the potential for extraterrestrial life. The journey to find the answer is a thrilling adventure, one that takes us to the very edges of our knowledge and beyond. So buckle up, it's going to be an exciting ride. The Drake equation, proposed by Frank Drake in 1961, provides a way to estimate the number of extraterrestrial civilizations in our galaxy. The equation is a fascinating concoction of variables, each signifying a different aspect of our cosmic quest. Let's break it down, shall we? First, we have the rate of star formation in our galaxy. This sets the stage, as stars are the cosmic cradles where planets and potentially life forms are born. Next is the fraction of those stars that have planetary systems. Not all stars are blessed with planets, but thanks to the Kepler Space Telescope, we've discovered that planets are more common than we once thought. Then we consider the average number of planets that could potentially support life per star with planets. This refers to planets residing in the Goldilocks zone, where conditions are just right for liquid water to exist. The following factor is the fraction of those planets where life actually develops. Here we delve into the realm of biology and the mysterious origins of life. We then consider the fraction of life that evolves into intelligent beings. Intelligence, as we understand it, is a rare and precious commodity, even on our own planet. Next, we look at the fraction of civilizations that develop technology that releases detectable signs into space. This is the point where a civilization graduates from being merely intelligent to being technologically advanced. The final ingredient in this cosmic recipe is the length of time such civilizations release detectable signals. This is perhaps the most uncertain factor of all, given the relatively short time we've been broadcasting our presence into the cosmos. Though it's more of a tool for stimulating scientific dialogue than a definitive answer, the Drake equation sets the stage for our exploration of space. It's worth noting that the Drake equation doesn't provide us with a concrete number. Rather, it's a framework for discussion and a reminder of the many unknowns in our quest for cosmic company. Whether we're alone or not, the journey of discovery is a remarkable one, and the Drake equation is our compass guiding us through the vast cosmic seas. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new possibilities in the search for habitable environments. These celestial bodies, found in the vast expanse of our galaxy, offer us a glimpse into a universe brimming with potential for life as we know it. The concept of habitability has, for a long time, been tied to the idea of liquid water, a crucial ingredient for life as we understand it. This has led to the identification of what we call the habitable zone, often referred to as the Goldilocks zone. This is the area around a star where conditions are just right, not too hot, not too cold, for liquid water to exist on the surface of a planet. The significance of this zone is monumental in the search for extraterrestrial life. If we find a planet in the habitable zone of its star, it might just have the right conditions to harbor life. But remember, being in the habitable zone doesn't guarantee that a planet is habitable. It simply means it's worth taking a closer look. Over the past few decades, we've discovered thousands of exoplanets, many within these habitable zones. Some of these distant worlds are similar in size to Earth, further piquing our curiosity. Could these Earth-like planets host life? We're still in the early stages of exploring this question. Using powerful telescopes, we continue to scan the cosmos, studying these exoplanets for signs of life. We're searching for indicators such as water vapor, oxygen, and methane in their atmospheres, the fingerprints of potential life. It's an exciting time in the field of astrobiology. With each new discovery, we inch closer to answering the age-old question, are we alone in the universe? The discovery of exoplanets and understanding of habitable zones have brought us one step closer to finding an answer. Our quest to find life beyond Earth is now more focused, thanks to our understanding of exoplanets and habitable zones. Life on Earth is incredibly diverse, even existing in the most extreme conditions. Consider the extremophiles. These are microscopic organisms that thrive in conditions most other life forms would find utterly inhospitable. From the scorching heat of volcanic vents on the ocean floor to the freezing cold of Antarctica's dry valleys, these hardy microorganisms manage not just to survive, but to flourish. Let's take a moment to appreciate the vast spectrum of extremophiles. There are thermophiles, which love high temperatures, and psychrophiles, which prefer the cold. Then we have acidophiles and alkaliphiles, thriving in highly acidic or alkaline environments, respectively. Even environments with high radiation or extreme pressure, which would be deadly for most life forms, are home to certain types of extremophiles. But what do these extremophiles mean for the search for life beyond Earth? Well, their existence broadens our understanding of the conditions in which life can exist. If life can evolve to survive in the harsh conditions on Earth, who's to say it couldn't do the same on other planets? Perhaps in the icy oceans of Jupiter's moon Europa, or beneath the surface of Mars, life in some form is waiting to be discovered. Moreover, these extremophiles could potentially be the key to decoding the mysteries of early life on Earth. By studying these organisms, we can get a glimpse into the primitive life forms that might have existed when Earth was a young, volatile planet. This could provide insights into the potential for life on other planets with similar conditions. So, the next time you imagine life on other planets, remember the extremophiles. These microscopic powerhouses challenge our preconceptions about where life can exist and open up a universe of possibilities. If life can thrive in extreme conditions on Earth, could it not exist elsewhere in the universe? Mars, our neighboring planet, has been a consistent point of interest in the search for extraterrestrial life. Its close proximity and similarities to Earth make it an intriguing candidate in the quest to find life beyond our home planet. Historically, Mars has been the focus of numerous missions, each one progressively unveiling the planet's secrets. The Viking missions in the 1970s were the first to search for direct evidence of life by looking for signs of microbial metabolism in Martian soil. Despite the inconclusive results, these missions ignited the curiosity that drives our exploration of Mars to this day. Fast forward to the 21st century, and our robotic explorers are more advanced than ever. Current missions like NASA's Perseverance rover and the European Space Agency's ExoMars program are equipped with state-of-the-art instruments to search for signs of past or present life. They're examining the Martian surface, drilling into its crust, and analyzing samples to detect organic compounds, the building blocks of life as we know it. But why is finding life on Mars so significant? Well, it's all about broadening our perspective. Finding life, even microbial, would mean that life is not exclusive to Earth. It would suggest that life can emerge in places beyond our home planet, and that the universe may be brimming with potential habitats. Moreover, discovering life on Mars would have profound implications for our understanding of biology. It could provide insights into the origins of life and the evolution of organisms in environments vastly different from our own. It could even help us prepare for the possibility of encountering more complex forms of life in our cosmic explorations. In essence, the search for life on Mars is more than just a scientific endeavor. It's a journey of discovery, one that pushes the boundaries of our knowledge and challenges our understanding of our place in the universe. Finding life on Mars, even in its simplest form, would revolutionize our understanding of life's existence beyond Earth. Beyond just finding life, we are also searching for signs of intelligent civilizations. This grand quest is spearheaded by organizations like SETI, which stands for the Search for Extraterrestrial Intelligence. SETI's primary goal is to detect deliberate signals from an alien civilization, signals that are intentionally beamed into space, like radio waves, for instance. Now, you might be wondering why we're on the lookout for radio signals. The answer lies in the fact that radio waves can travel vast interstellar distances without much interference or loss of information. They're like cosmic postcards, delivering messages across the cosmos. But here's the tricky part. Space is mind-bogglingly vast, and we're tuning into a cosmic radio dial that spans billions of frequencies. Detecting an alien signal isn't just about having the right technology, it's also about searching in the right place, at the right time. And then comes the challenge of understanding any signals we might find. Just think about it. These potential alien civilizations could be millions of years ahead of us in terms of technology and evolution. Their language, their way of thinking, their entire concept of communication might be radically different from ours. So we're not just searching for a needle in a haystack, we're searching for a needle that we might not even recognize when we see it. Despite these monumental challenges, the search continues. SETI and other organizations use arrays of radio telescopes, scanning the skies for signs of extraterrestrial technology. They're also developing new methods, like looking for laser pulses or signs of massive engineering projects that could alter a star's light. The search for extraterrestrial intelligence is an endeavor that combines the best of our creativity, our technology, and our unyielding curiosity. It's a search that invites us to ask big questions about who we are, where we come from, and whether we're alone in the cosmos. The search for extraterrestrial intelligence is as complex as it is exciting, with new developments constantly on the horizon. Despite the high probability of extraterrestrial life suggested by the Drake equation, we have yet to make contact. This is the essence of the Fermi paradox. Named after physicist Enrico Fermi, this paradox is a question that has stumped scientists and space enthusiasts for decades. According to the Drake equation, there should be a high probability of intelligent life in our galaxy, yet we find ourselves seemingly alone. The universe is almost 14 billion years old, and our galaxy, the Milky Way, is about 10 billion years old. With billions of stars similar to our sun, many of which are much older, it stands to reason that there should be civilizations far more advanced than ours. If these civilizations exist, why haven't we heard from them? This is the crux of the Fermi paradox. Some suggest that perhaps advanced civilizations are avoiding contact, or maybe they've self-destructed before reaching a point where they could communicate with us. Others propose that we are indeed receiving signals, but they're so advanced or so unlike anything we're familiar with that we simply don't recognize them. Or maybe we're just not listening in the right way or at the right time. There's also the possibility that we are, in fact, alone. Maybe the conditions for life as we know it are so incredibly specific and rare that we're the only ones who've managed to beat the odds. These theories and more make the Fermi paradox a fascinating topic of discussion. It's a reminder of how much we don't know about the universe and how much more there is to discover. It's a paradox that pushes us to keep exploring, to keep questioning, and to keep reaching for the stars. The Fermi paradox remains one of the most intriguing puzzles in our quest to understand our place in the universe. Studying the atmospheres of distant exoplanets can provide clues about the potential for life. To understand this, let's delve into the realm of biomarkers. Biomarkers, or biological markers, are substances indicative of life processes. In the context of exoplanets, these are gases in a planet's atmosphere that could potentially indicate the presence of life. This might sound a bit like looking for a needle in a cosmic haystack. After all, we're talking about analyzing the atmospheres of planets light years away from us. But thanks to the advances in technology and the dedication of brilliant minds, we're making strides in this field. One way we study exoplanet atmospheres is through a technique called transmission spectroscopy. When an exoplanet passes in front of its host star, the starlight filters through the planet's atmosphere. By analyzing this filtered starlight, scientists can identify the gases present in the planet's atmosphere. Oxygen, for instance, is a key biomarker. On Earth, photosynthetic organisms like plants and algae produce most of our oxygen. If we detected significant amounts of oxygen in an exoplanet's atmosphere, it could suggest the presence of similar life processes. However, it's not as straightforward as it sounds. Non-biological processes can also produce oxygen. So scientists look for a combination of biomarkers. Finding oxygen along with methane, for example, would strengthen the case for life, as these gases quickly react with each other and would need a continuous source, potentially life, to persist in the same atmosphere. And it's not just about finding life as we know it. By studying exoplanet atmospheres, we also hope to learn about potential life forms that might be vastly different from what we're used to. Life that thrives in extreme temperatures or under high pressures, or even life that breathes different gases. The study of exoplanet atmospheres is a fascinating and complex field, filled with possibilities and challenges. But every discovery, every piece of data, brings us a step closer to answering one of the most profound questions. Are we alone in the universe? As we continue to study exoplanet atmospheres, we inch closer to finding signs of life beyond our solar system. Enceladus and Europa, moons with subsurface oceans, hold intriguing possibilities for life. As we move away from our home planet, our gaze turns to the moons of the gas giants, Jupiter and Saturn. Enceladus, a moon of Saturn, and Europa, a moon of Jupiter, have become points of interest in our quest to uncover life beyond Earth. These icy moons might seem inhospitable at first glance, with their surfaces locked in a perpetual winter, but beneath their frosty exteriors lie vast oceans of liquid water. These subsurface oceans are kept warm by tidal heating, a process where the gravitational pull of their respective planets causes the moon's interiors to flex and heat up. Recent discoveries have added more fuel to the fire of our curiosity. NASA's Cassini spacecraft detected plumes of water vapor and organic molecules erupting from cracks in Enceladus's ice. This suggests that not only does Enceladus have a subsurface ocean, but it may also have the necessary ingredients for life as we know it. Europa, too, has shown signs of geysers erupting from its surface. The Hubble Space Telescope has provided us with evidence of these water plumes. If confirmed, this could mean that Europa's ocean isn't locked away beneath miles of ice, but is interacting with the surface, making it much easier for us to study. These discoveries on Enceladus and Europa have profound implications. They suggest that life might not be a phenomenon exclusive to Earth, but could be a regular occurrence wherever the right conditions are met, even in the cold depths of space. It's a tantalizing prospect that redefines our understanding of where life could exist. As we continue to explore these fascinating moons, who knows what we might uncover? Each new discovery brings us one step closer to answering the age-old question, are we alone in the universe? These moons remind us that potential for life may exist even in the most unexpected places. The search for extraterrestrial life is a profound journey of discovery and understanding. We have delved into the possibility of life beyond Earth, starting from the Drake equation, which estimates the potential number of civilizations out there in the cosmos. We've explored the concept of exoplanets and their habitable zones, places where life as we know it could potentially exist. We've examined life's resilience on Earth, with extremophiles thriving in harsh conditions, hinting at life's potential to exist in unexpected places across the universe. Our quest has led us to Mars and beyond, searching for microbial life and the subtlest signs of existence. We've sought out signals from other civilizations and grappled with the Fermi paradox. We've considered the atmospheres of distant exoplanets, looking for signs of life in their chemical makeup. And finally, we've ventured to the moons of Enceladus and Europa, with their subsurface oceans potentially harboring life. As we continue to explore the universe, we may one day answer the question, are we alone?